Okay, so Miss Gallus apparently either really sucks at basketball or people doesn't don't believe her, right? Because like this is like the fourth lesson I think we've been on her. So recall that Mrs. Gallus claims she is an 80% free throw shooter, like she swears. Okay, Mr. Wilcox is skeptical and believes that she is less than 80% free throw shooter. Mrs. Gallus has decided to take another simple random sample of 50 free throws to prove herself. This woman will not give up. So, what is the null hypothesis? What is the null hypothesis? HO is P equals 0.8. Okay. Now, what's the alternative? What's Mr. Wilcox say? He's like, bro, she sucks. So less than 0.8, right? And what does right? He's such a hater. All right, so P is equal to the true proportion of what? Of free throws made by Miss G. Okay, yesterday we talked about type 1, type 2 error. Okay, so looking back to those notes, describe a type 2 error in this setting. Remember, that's the one with the alternative hypothesis, but not having evidence for the alternative hypothesis. With me? Okay, so what is the alternative hypothesis? Okay, so Miss G is less than 80% free throw shooter, but we fail to reject, we fail to find convincing evidence. To find convincing evidence that she is less than 80% free throw shooter. Okay, so Miss G is less than 80% free throw shooter, but we fail to find convincing evidence that she is less than an 80% free throw shooter. Yeah? Gucci? Okay, here's where it gets crazy. So suppose that Mrs. Gallus's true free throw percentage is actually 66%. Wow, what a failure. So the alternative hypothesis is true. Enter all the information into this applet and then click on display type 2 error. It'll show as a blue shaded region. Okay, so I'm gonna do it for you so you don't have to. You're welcome. HTTPS. iStats. Probably that. We're gonna go with that. Okay. Respectfully, lazy at 7 o'clock in the morning. Okay. So what was the null hypothesis? 0.8, right? Okay. Are we doing type 1 error or type 2 error? Type 2 error. The alternative hypothesis, is it less than, greater than, or two-sided? Okay. What was the true value? Sorry, true value we got. It was, there it is. Okay. And then what was our sample size? Do we remember? Okay. And then type 1 error alpha, we're keeping that at 0.05. Yes? Okay. Look at my graph. This is type 2. Okay, so draw your shading. Draw your shading on this. Huh? Oh, but you're fine. Right in here, type 2. It's already there? No? Okay. Bro, I did the whole thing for you. Type 2. Put it in that little shaded region. Okay. This little like doodad is that the HA is true. This little doodad is that the HO is true. All right, remember your p value is 0.66. That's what they tell us, right? And we're going to draw just like a straight line fill in. So it makes it really easy for us to see the middle. Okay, the type 2 error is that blue shaded region. All of the white junk to the left of that is the power. The power. All right, on number 3, on your question number 3, for power, there must be a specific value for the alternate. So HA is equal to 0.66, which is P. Okay, so if the HA is true, what is the probability of an incorrect decision? So what is the difference? Go ahead. What do we got? So if HA is true, what is the probability of an incorrect decision? 0.2. How'd you get that? Okay. Is the shaded region specifically the type 2 error? Mm-hmm. Okay, so where is this little part right here? What number is this one now? 0.76. Okay. Not the short. Not the short. Like 1-ish. Yeah. Okay. So this shaded region, it goes from here to over here, right? Okay, but where does it end? Okay, so how can we figure that out? There's always a math way to do it. So you could find the z-score, you could do the whole distribution, you could actually draw it out, right? On the normal curve so that way you knew where it kind of like ended up. Okay, obviously we're looking at some janky graph, but it's okay. All right, so really quick, this is describing a type 2 error, right? Part A. And part B is describing the power. Okay, so this goes all the way up to like 0.9, right? Okay, so from our p-value, which was 0.66, right? All the way up to 0.9. All right. That little like shaded region is going to be 0.24. And if the HA is true, what is the probability of a correct decision? Well, what's 1 minus 0.24? 0.76. So power is what's left over after the type 2 error. Okay. So when we do the probability of the type 2 error plus the power, that's the combination of the whole thing, right? Yep. Go ahead.
Okay. What defines the boundary?
So we go from the p value, so the one that we have established, which is that 0.66, all the way to the end of the alternative hypothesis, right? the end of the alternative hypothesis. So what makes that HO true? What makes the null hypothesis true? What makes the null hypothesis true? What was the null hypothesis? Okay. So once we hit 0.8, like that's the null hypothesis, right? So then that means that the alternative is not true then. Yes? 0.8 is that the HO is true. Okay. For a type 2 error, what's the definition? What did we just go ahead?
So because like our null hypothesis is in that like in between area between like two exists, because like it's a part of like the unit curve of the alternative hypothesis. That's where you get like these sentences because we have that overlapping area. And so if we have that overlapping area, we have an overlapping possibility too. Because it's like you know the area of the normal curve is probability. And then we have the blue normal curve, which represents our alternative hypothesis, and then the red normal curve, which is the null. But because we have that overlap, there's a chance for like it not to go away, which is the area where our type 2 error exists.
So why could this be the reason? You have embedding overlapping of A of one of one comprehensive. So why that there? Starting to say one person exists. Right, and so the intersection.
You're saying from here. Why is it from here to here? It's fair because it should have been from here over, right? I think this should be moved over. Because this right here should be the where this ends minus your p-value. So graph is wrong? I would assume. Because this should be over a little bit more. Yeah.
Part where it's like above the number plate, like yeah, like that stuff is probably just supposed to be people.
So I'm like, it doesn't make any sense.
So like the only reason that like the height exists is because of how frequently it occurs, not necessarily the number itself. So it's more like ignore the curve part of it to know that it's like a flat like 2 lines or whatever that is. Like you need to know the frequency.
Not talking about that yet.
Yeah.
Yeah.
That's like really the, at least for now, we're not really talking about the frequency of time, we're just saying,
It's what's the area of underneath this curve.
you know,
It's not just these numbers between here to here. We're getting there. All right. So looking back at number or part C, interpret the probability of this correct decision in the context of the problem. So if Miss G is a 66% free throw shooter, there is a 0.76 probability. Oh my God. Is a 0.76 probability. The significance test will find convincing evidence to reject the null. that she is 80% free throw. So what power does is, I mean, it does just that. It gives you power to either reject or fail to reject. So looking at this, if she actually was a 66% free throw shooter, there's a 0.76 probability the significance test will find convincing evidence to reject the null that she is an 80% free throw shooter. We took 0.9 and subtracted 0.66. So where it ended to that little part right there. Yep. Okay. So we're gonna hit click display power. And back to this. You see where it's at? And it actually calculated it up here for us. Yay. Okay. Where does it say display power? There it is. Boom. So green shaded region is the power. Okay. We want to increase the power of our test. So how can we adjust each of the following factors to increase our power? If we take our sample size and we increase our sample size, watch what happens. What happened to our power? It got stronger. So an increase in sample size, it also made it super skinny, right? So there's less variability. Okay, so for sample size, if we increase our N, then we get lower variability. And notice how like the distributions also decreased in their crossover. The distributions decrease in their crossover. Decrease in crossover of distributions. Which means that type 2 doesn't really happen. When your HO and your HA are completely different and spread it apart, your type 2 error, you're not going to have as much. Okay. If we increase the alpha, so let's move this guy back. If we increase the alpha, what happened? All right, so if we increase the alpha, if we increase the little fish looking thing, the power requires us to reject the null. Bless. So if you increase the alpha, you increase the probability of rejecting null. So watch it again. If we go from here to up here, okay? And then if we have an alternative P, if we decrease our P value, then we increase the distance from the null. If we decrease our P value, we increase distance, bless you, distance from null. All right, flip over to the back. Okay, so let's summarize this. But it's so much fun. Okay, these little stupid tables that we talked about yesterday. So we've got type 1, we've got power, we've got a smiley face. I'm going to tell you the outside in just a second. And then we got type 2. Okay, so if the HO is true and we reject the HO, we got a type 1 error. If the HA is true and we reject the null, then we have power. This one doesn't matter. If we fail to reject, then we get a smiley face. Okay. Then over here, we have an HA is true, and we fail to reject the null, then we get a type 2. All right, so power. That means that we look at the probability of rejecting the null, given that the HA is true. If HA is true, context, there is a power probability of finding convincing evidence to reject null in context. Now remember, your type 1 was alpha. Your type 2 is 1 minus your power. So yesterday we didn't talk about how to get your type 2. We only talked about your type 1, right? Type 2 is 1 minus power. They must tell you the power. Yes? Called the what? Power. Yeah. Okay, so to increase power, we can increase sample size, we can increase our alpha, or we can increase the distance to HA. Okay. All right, go ahead and take a look at your check your understanding. Take about 5 minutes, and then we're going to talk. Okay. All right, let's chat about it. High school student is planning a very large graduation party. She needs to know how many people are planning on attending in order to estimate the cost of the party. She plans to select a random sample of 25 guests that were invited to the party and record whether or not the person plans to attend the party. She will then test the null hypothesis is P equals 0.75 versus P does not equal 0.75, where P is the true proportion of all invited guests that will attend the party. She'll use an alpha of 0.05. So, suppose the true proportion of invited guests that will attend the party is 0.7. Then the power of the given significance test is 0.1. Interpret the power. So all you're going to do is make that little statement that was up at the top. So if the true proportion of all invited guests, if the true proportion of all invited guests that will attend is 0.7, there is a 0.10 probability of convincing evidence to reject null. that 75% will show up. So if the true proportion of all invited guests that will attend is 0.7, there is 0.10 probability of convincing evidence to reject the null that 75% will show up. So find the probability of a type 1 error, find the probability of type 2 error for the test in part A. So probability of type 1 error is your alpha. What's your alpha? Okay, probability of type 2, that's 1 minus power. They told us our power is 0.1, so 1 minus 0.1 is 0.9. We okay on B? Nothing too crazy. Most people mix those up, so don't be that guy. All right, determine whether each of the following would increase or decrease the power of the test. Explain your answers. So going from 0.05 to 0.01, would that increase or decrease the power? Okay, why? Okay.
Because the probability of the type 1 error is.
And what does alpha do?
Alpha is the number of less than or to 4. Yeah.
4.
This is evidence that we can reject the null analysis.
Okay, so it's harder to reject the null.
Yeah.
So the smaller your alpha is, the harder it is to reject the null. Using n equals 100 instead of n equals 25, that's going to increase the power, right? We increase the sample size because your variability will decrease. So you increase your sample size, you decrease your variability. Because think about it, the more people that you know about, you're getting true, like closer and closer to the really true proportion, right? Yeah. I mean, the more, like, again, the more you know about your population, better off you're going to be, right? And it's going to get hopefully closer and closer together. Okay. Good. All right. I'm going to give you just a little while to look over 9.1 to 9.3. That is all this quiz is over. On the quiz, there are, no, just 9.1 to 9.3. Yeah. Okay. So it's 1 to 6 questions. It's not too bad. It really isn't. So look over your 9.1 to 9.3 notes. I'm going to give you about 9 minutes, and then we're going to take our quiz, and then we'll be good to go.